50 years ago, the Apollo program sent humans to the moon for brief visits. The upcoming Artemis missions have a different objective: building a permanent city on the surface. The immediate barrier to building anything in space is the launch cost. Sending a single ton of drinking water or building supplies into orbit runs between $2 and $5 million. You cannot economically ship a functional base across 239,000 miles of space. To survive, engineers have to rely on in-situ resource utilization, which simply means building and living off the local land. This forces a major geographic pivot. Apollo astronauts landed on the flat, predictable terrain of the lunar equator. Artemis is targeting the deep, highly jagged terrain of Shackleton crater at the moon's south pole. To build a permanent outpost, engineers must abandon the safest landing zones on the moon and drop directly into its most extreme environments, because that is the only place the necessary resources exist. This 3D model compares Earth's tilt to the moon's. Earth sits at a 23.5-degree angle, giving us our seasons. The moon barely tilts at all, just 1.54 degrees. Because of this, the sun never climbs high into the sky at the Lunar South Pole. It just crawls endlessly along the horizon, continuously illuminating specific mountain rims to create peaks of eternal light. But right next to those sunlit peaks are deep crater floors. Because the sunlight comes in at such a flat angle, it never reaches the bottom of these depressions. These valleys have sat in pitch-black darkness for over 2 billion years. Inside these permanently shadowed regions, temperatures sit lower than minus 328 degrees Fahrenheit, cold enough to freeze oxygen solid. And mixed into the dirt inside these dark traps are billions of metric tons of frozen water ice. The peaks provide near-constant solar energy, and the valleys hold massive reserves of raw matter. The two absolute requirements for an off-world settlement sit right next to each other. On Earth, water is something we drink. On the moon, it acts as the primary industrial raw material for an entire base. This schematic animation shows electrolysis. Running an electrical current through melted lunar ice splits it into hydrogen and oxygen. That oxygen provides breathable air. Recombining them creates hydrolox, an efficient chemical propellant allowing spacecraft to refuel directly on the moon. It also provides a structural defense. Space is saturated with lethal cosmic radiation. By packing extracted water into storage tanks surrounding the walls of a human habitat, it acts as a dense, highly effective physical shield against those incoming cosmic rays. Mining water yields breathable air, rocket fuel, and radiation protection, all from a single source. It is the ultimate logistical cheat code for off-world engineering. But before engineers can harvest that ice, they have to navigate the lunar regolith. This is the technical term for moon dust, and it is a jagged, electrically charged powder created by billions of years of meteorite impacts pulverizing the rock into tiny glass-like shards. It sticks to spacesuits and severely degrades machinery. During Apollo 12, the lander's exhaust blasted this dust outward like high-velocity shrapnel, causing severe surface damage to the nearby Surveyor 3 spacecraft seen here. This creates an engineering paradox. To prevent descending rockets from blasting regolith into your base, you need a solid landing pad. But to build a landing pad, you need to land heavy construction equipment first. You also cannot pour traditional concrete. The moon's lack of atmosphere means any liquid water you mix into cement will instantly boil away into vapor or freeze solid. If engineers cannot invent a way to harden the lunar surface using only the native dust and zero liquid binders, the regolith will permanently halt human expansion. NASA's solution is Project Olympus. The concept is to weaponize the iron-rich dust against itself using extreme heat instead of liquid water. High-powered lasers heat the surface, melting the outer edges of the dust particles. They fuse into a solid, concrete-like structure through a process called sintering. Before human crews arrive, robotic rovers equipped with these lasers will roll across the dirt. They will melt the regolith layer by layer, autonomously 3D printing flat, hexagonal landing pads. Once the landing zones are secure, those autonomous printers can build out the rest of the architecture. They will shape blast walls to protect equipment, lay smooth roads for rovers, and print thick, curved habitat shells to block radiation. Sintering transforms the moon's deadliest hazard into the physical bedrock of a permanent settlement, allowing humans to pave roads and print shelters without a single shipment of Earth-made concrete. Living inside those printed walls will lack the romance of space tourism. The first lunar citizens will face grueling 6 to 12-month deployments, operating out of personal quarters roughly the size of a walk-in closet. Because the moon has only 1/6 of Earth's gravity, human bones rapidly lose density and muscles weaken. Crews will endure mandatory, non-negotiable 2-hour daily workouts just to keep their bodies intact. Every resource requires strict conservation. The water flowing out of the base's taps will be molecularly purified, which is a polite way of saying the crew will drink recycled moisture recovered directly from their own sweat and urine. The lunar surface will not be a playground. It will operate as a highly regimented industrial endurance test against deep isolation and physical decay. So why put humans through all of this danger and torment just to build an industrial plant on a lifeless rock? This bar chart compares the energy required to launch a payload from Earth versus the moon. Escaping Earth's crushing gravity takes an enormous amount of fuel, but the moon's gravity well is shallow, requiring a tiny fraction of that energy to reach orbit. Because of this, a spacecraft heading to Mars can launch from Earth relatively empty to save money. Once in orbit, it can stop at the moon, fill its tanks with lunar-mined hydrolocks, and begin its deep space journey fully stocked. Shackleton Crater will function as a strategic off-world gas station and construction yard, providing the exact infrastructure needed to travel deeper into the void. Turning the moon into a self-sustaining industrial hub provides the foundation required for humanity to launch towards Mars and reach the rest of the solar system.